If the occurrence of one event does not affect the probability of a second event occurring, then the two events are independent events. Independent events are those events that occur one after another, whereas the first event does not affect the second event. For example, rolling dice. When you roll a die, it doesn't matter what you get on a previous roll, the probability for the next roll is always going to be the same. That's different than if you're playing most card games, where if you get dealt a certain card, that means your opponents cannot get that card, so that their probability is affected by what you have in your hand. Regardless whether they're independent or dependent events, the probabilities are both found the same. To find the probability of two or more events occurring, you just multiply the probabilities of each individual event separately, and that'll give you the probability of all of the events occurring. This can be extended to happening to three or more independent events as well. So the first example is that a coin is tossed and a number cube is rolled. Find the probability that the coin lands on tails and the die rolls a 3. So we're trying to find the probability of tails, then a 3. So the probability that tails happens would be 1 out of 2. One side is a tail out of the 2 total sides. We would take that times the probability of rolling a 3. The probability of rolling a 3 is 1, 3 on a die out of the 6 total sides, and 1/2 times 1/6 is 1/12. You can actually see that with the sample space. If we listed out all the possibilities, so in other words, heads 1, heads 2, heads 3, heads 4, heads 5, heads and 6, and then compare that with tails 1, tails 2, tails 3, and so on, you can see that there are 12 combinations of possibilities for flipping a coin and rolling a die, and of those 12, only one of them is tails 3. So that's another way of showing that it is 1 out of 12, although I think it's much easier if you find the probabilities individually and then multiply them. Like I said earlier, dependent events is when the first event does affect the probability of the second event occurring. They are dependent events. For example, if we're asked to find the probability of drawing a jack and then a queen. So the probability of drawing a jack is 4 out of 52. There are 4 jacks in a deck of 52 cards. But if you get the jack and then you need to find the probability of getting a queen now, there are still 4 queens left in the deck, but there's only 51 cards left in the deck. So your probability of getting a queen is going to be different than getting a jack because there are now fewer cards left in the deck. You still figure that out by multiplying them together. So the notation, when it says probability of A and B equals the probability of A, and then it's got that vertical line in between the B and the A on the second part, that just means the probability that B occurs given that A has already occurred. And again, this can be extended to 3 or more dependent events. So you're still multiplying to find the probabilities. So if a bag contains 12 reds, 9 blues, 11 yellows, and 8 green marbles, 2 marbles are drawn at random and not replaced, what's the probability that a red and then a blue is drawn? So we're trying to find the probability that we get a red and then a blue. There are 40 marbles in this bag. We can see that by adding all the marbles of each color together. There are 40 marbles. The probability that you get a red is going to be, there are 12 red marbles in the bag out of the 40 that are in the bag. That actually simplifies to 3/10, and I would suggest simplifying. It should make your multiplication a little easier. And then we're going to take that times the probability that we get a blue marble. There's only 39 marbles left in the bag now because you drew a red one out. There are now 9 blue marbles in the bag. That simplifies to 3/13. And then when we multiply 3/10 times 3/13, we get 9 over 130. That is a little less than 7%. You're going to see that on a lot of these multi-events that you're going to get some fairly small fractions or some pretty small percentages. We can extend this to the idea of playing cards as well. So let's say, for example, we want to find the probability that you're given two cards in your favorite card game, and we want to find the probability that both of them are aces. So the probability that you get the first ace would be 4 aces out of the deck out of 52 unknown cards. And then we would take that times the probability of getting an ace on the second draw. If you get an ace on the first draw, there are now only 3 aces left in the deck, times there are now only 51 cards left in the deck. If I simplify those before multiplying, I get 1/13 times 1/17, and that is 1 out of 221 times you can expect in a card game that your first 2 cards are both going to be aces. Sometimes a question might ask you to find the probability of one of the simple events if you've already been given the probability of the whole compound event. At a restaurant, 25% of customers order chili. If 4% of the customers order chili and a baked potato, find the probability that someone who orders chili also orders a baked potato. So remember that the probability formula for any multiple events is the probability that A occurs times the probability that B occurs, and that is going to equal the probability that both occur. So if it says 25% of the customers order chili, we can write that as 0.25. But then it goes on to tell us that 4% of the customers order chili and a baked potato. It has actually now told us the probability that both occur. So that 4% is actually going to be what it equals. And I change that to a decimal, so that's 0.04. What we're trying to figure out is what is the probability that someone who ordered chili also gets a baked potato. We're trying to figure out now what's the probability that a baked potato is ordered. That's the unknown, and that's the x. So again, this one has the probability told us of both. We want to find the probability of one of the singular events. And we would solve this one, since it's 0.25 times x, that's 0.25x equals 0.04. We would divide by 0.25. And 0.04 divided by 0.25 would give us x equal to 0.16, or about a 16% chance that a customer in this restaurant orders a baked potato. Probabilities can also be applied to two-way frequency tables. It's just something that we have done in a previous class. With two-way frequency tables, not all the totals are going to be the same. You have to figure out which total we want to base the probability upon. A drug company conducted an experiment to determine the effectiveness of a certain new drug. Test subjects were randomly assigned to one of two groups, a treatment group, which received the drug, and a control group, which received the placebo, which is a sugar pill or a fake drug, in place of the drug. The contingency table shows the results. So part A is find the probability that a test subject's condition improved given that he or she was in the treatment group. So we're looking for the cell that contains a test subject's condition improving given that they were in the treatment group. So that's this 1600 right here. There are 1600 whose condition improved given that they were in the treatment group. We're going to put that over the total number that were in the treatment group, given that he or she was in the treatment group. So we're looking for the total that was in the treatment group. The total that's in the treatment group is going to be this row right here, and there are 2,000 in the treatment group. So it'd be 1,600 over 2,000, and that would simplify to 4/5, or about 80%. Part B asks you to find the probability that a test subject was in the control group, given that their condition did not improve. So control group and not improving is this cell right here that I'm kind of highlighting. It's the 800. That is control group, did not improve. We're going to put that over, and on this one it says given that his or her condition did not improve. So that is actually the total of this column right here. Condition did not improve. 800 over 1,200, and that would be 2/3, which is approximately 66.7%.